Okay, good afternoon, everyone. Yeah. So, and hope you have a good week. And in this lecture, we're gonna continue learning our reinforcement learning knowledge. Okay. So in the last lecture, so today, the outline for today, we first review what we have learned in the last lecture. Then we go to two types of approaches: dynamic programming and Monte Carlo methods. Okay. First of all, let's review what we learned before. So I guess we're gonna look at this diagram, this framework again and again in this lecture. Okay, as we remembered in the last lecture, we so you always need to remember that we have an agent, we have an environment. The agent need to interact with the environment. The agent receive the state and a reward from the environment, and agent make the action based on the policy which is we use the pi to represent the policy. Okay. So for this policy, actually, we design some functions to decide what kind of the status and what kind of the actions need to take. So in that case, we define the state value function and action value function, right? State value function, action value function. State value function, we use the V to represent the state function, and the action value function, we use the P, right? The P to represent. So then through this process, the policy can be updated and the state is also updated. Then eventually we get the better performance. Then the general objective is that we need to maximize the return, which is a cumulative reward from the environment. So in the last lecture, we learned this k-armed bandit problem. You may remember. So assume that you have multiple machines, then you need to choose which one you will pull down the arm. Then you need to repeat this process again and again. Eventually, you need to decide which one is the machine that has a maximum expected reward for you. So after each choice, we receive a numerical reward from a stationary probability. So then for this multi-armed bandit problem, the thing is that we don't know the distribution behind each arm, okay? Behind each arm. So then we need to repeat to try to get the experience of those machines to know their distribution. So our objective is similar, maximize the expected total reward. Then what we do is that we design some algorithm to repeatedly and get the reward, and eventually we calculate the average, right? The simple way. So this is a simple the algorithm we design. We initialize with the reward equal to 0 and step size. Then there is so we also introduce so-called epsilon greedy algorithm, because just in case that we keep trying a particular machine or the distribution, but we've just forgot to explore other possibilities. There could be some chances that another machine has a higher probability, has a higher expectation. So that's why we introduced this epsilon greedy algorithm. So what we do is that before we run this greedy algorithm, we first check the probability. If we have a small probability to do random selection, if we don't fall into that probability, then we just do the greedy algorithm. So in this case, we kind of balance the exploitation and the exploration. Okay, as we mentioned in the beginning of this lecture, there's always the trade-off between exploration and the exploration. Then eventually we just calculate the average return we got, accumulated return, right? So you have the return R, and so this is the summarized way to calculate the return. You have this return minus the current average, the previous calculated, the quality of the action. Then you just get the error, we call it error. Then with the error, we do the average plus the current quality of action, then update this QA. So we just loop continuously. If you loop enough time, then you will gradually get to the expected result. Then you will know which one you need to choose, right? This is a map problem. You can also call it multi-armed bandit problem, MAB, map problem. After that, we come to this sequential decision making with Markov property. When we call the sequential decision making, if it follows the Markov property, then we call it Markov decision process. And with the finite status, then in short, we just call it finite MDP. In this process, you have multiple status. Then you have from one state to another state, you can jump with some probability. If you choose a particular action, then that action will give you some reward, right? Then based on those process, we develop this Bellman equation. With this Bellman equation, it basically tells us that we can calculate the state value of a state, right? The value of a state based on the neighboring state information. So you have if you want to calculate the state, S means a state, the value of a state, then you can just use the sum all the possibilities of actions and times with the neighboring states, right? S prime means a neighbor state. So after that, you just updated the current, your state's value, okay? We use VS, V means value, right? V pi is a particular policy for this state, yeah. Then this state can be changed, right? So then for all S belongs to S, so this S shall include every state in this environment. After that, we also come to this Bellman optimality equation. Optimality, BOE, in short, BOE, it also has two functions. One is a state value function, the other one is action value function. Sometimes people also call it state action value function because inside of this function, there's also state and action. So the difference is that state value function only has a state. The action value function has an action. So it's like the updated value for a state after an action. Okay. Instead of using the difference is that instead of check every possibility of the neighbor states, we just select the maximum one among those neighbor states. Okay, what do we call? We use the max. So it means that actually there are multiple choices here. Then we select that has the maximum value. Then to update the states of the value of the state. Accordingly, so we can also update the policy with the action, right? So with the maximum action. So as a diagram, as a explanation or describe, you can consider that the BOE so the left-hand side is the state value function, right-hand side is the action value function. So you have a state. Then now your purpose is that you need to choose which state you need to choose to update myself. So you just select the maximum one. Then you just choose one. Previously, we need to calculate all three branches. Now we just select one and to update the value of state. Then if you consider the action value function here, after you select so remember that the circle, the white circle is a state. Solid circle is the action, okay? once you select the action, then you after the select action, you update your status. Then you need to make the decision, update your policy. For that policy, you just select the policy that can maximize the value what you have. Okay, then you just select either one, not instead of calculate all the possibility. Previously, we need to sum all the possibilities. Now we just select the maximum one. Okay, we will look at it later. Then, based on this BOE, so actually you see here state value function. So you generally, if you if you have an environment that has many states, and each state has a value, then you can build the linear system, right? And the equation, the system of linear equation, BOE. Then you can just solve, because you see here, the unknown, the variables we need to get is the VS and the VS prime. Okay, these two are unknown. Then you just list all the, so you need to name the S0, so the neighboring, the state maybe S1, 2, 3. So it's like, for example, here you need to list 25 equations of BOE. Then to solve this linear equation, eventually you can get every unknown variables value, right? So this is what we checked in the last lecture. So we have this grid word. They have some particular setting. For example, if you are in the state A, whatever action you make, then you just jump to the A prime with the reward plus 10. Similarly, B, whatever action you make, you will just jump to B prime with the reward plus 5. So with this kind of setting, so if you hit the wall, then there's a -1 the punishment. So if you just based on this setting and build the linear equations like a matrix, then you just solve the matrix, then you just get all the values here. Based on this, all the values, you can just easily to make the update the policy. Okay, the policy, if you check here, for example, obviously the state A is the ideal state we want to stay, right? Because it has the highest state value. With this state value means that if you are staying here, you get the maximum reward. In other places, for example, you happen to be this on the corner side, then you want to get the maximum your reward. You can have either two choices, left and right. You can choose upper and upper, upper and right, or either this way. So actually, if you look at this grid word, it seems very simple and dummy like a result, right? But if you extend it to a very complicated world, a real world problem, it will become much complicated. So we'll look at some example later. So then the thing is, the problems with BOE is that we need to know the dynamics of environment. So it means that all those probabilities like transition probabilities and the actions probability, all those information need to be known. So most of the time it's difficult to know. And the computation resources need to be sufficient to complete the calculation, because every time we need to calculate the linear equation. So it's like we need to, if the state is super huge, if this linear equation has a very large content, then you need to calculate one by one, and it costs a lot of time. Okay, if the state has changed a little bit, then you need to recalculate again. So usually the environment has been keep changing, right? You need to calculate again and again. Actually, maybe last year or last year, I don't remember which. One research group published a paper in the Nature or Science, I don't remember. So they just improved this linear equations performance, like improved a little bit, but it's already very big jump in the area. So if you can improve this calculation of linear equations, they kind of improve the overall performance a lot. But in generally we can only rely on some existing approach to calculate those results. Then the third one is that A state should have Markov property, means that the current state only is decided by the previous state, not by the previous state, by the history, all the history, right? But sometimes this property is not hold. Yeah, as I mentioned here, though if we have super huge number of states, it may takes 1,000 years to solve those BOE. And solution, there are many solutions, approximation methods, heuristic search method, dynamic programming, and so on. So today we're gonna look at dynamic programming. Actually, in the last lecture, I already showed you how we can use Spearman equation to gradually calculate the state value function and update the policy. Actually, the dynamic programming just use those kind of iterative process to calculate, to update the state value. Okay. Dynamic programming in RL. So far, any questions for the last lecture? Okay. Dynamic programming. So I believe all of you have learned the algorithms course, right? In the algorithm, the introduction to algorithm, the DP is one of the major topic. So actually I already listed the property of the DP. What is the DP? Dynamic programming. Actually, it's just need to have two features. One is a subproblem overlap. So it means that you have a target problem you need to solve. This problem can be divided into subproblems. Then subproblems you can also be divided into subproblems. So among them, they have actually overlapped problems. Means that if you solve some part of the problem, you don't need to solve others remaining subproblems because the problem has been solved, calculated. You just save those data there and directly use those calculations. Then another feature is that you should have the optimal substructure property. So in the DP, actually, I don't want to prove that. Actually, in the DP, there is a formal proof for this optimal substructure property. Why this optimal substructure is important for the DP? Because you need to guarantee if you solve the subproblem, then the subproblem can serve the purpose of the target problem. Okay, that's the purpose of the optimal substructure property. Actually, usually they use those graph algorithm to prove this optimal substructure property. In that the subproblem, or like for example the shortest path problem, from the source to the destination, there could be so many passes to reach the destination. Then you need to, the target is that how you can calculate the shortest path to reach that destination. Then actually when we calculate shortest path, we need to divide the shortest path into multiple small sections. So then we just want to know if each section has the shortest path or the optimal solution for this overall problem. So then there's a formal proof for this optimal substructure. If you want to review, you can check the previous lecture, Introduction to Algorithm. So there's a proof process. But eventually the DP has this kind of two features, subproblem overlap and optimal substructure property, okay? So as an example, we usually use this simple example, Fibonacci series. So what is a Fibonacci series? So so we need to calculate the one number is a summation of the previous two numbers, okay? So the fn equals fn minus 1 plus fn minus 2. Now what is the result of f20? So I give this diagram. So it's not that difficult to see that if you want to calculate f20, you need to get the f19 and f18, right? For calculate f19, you need to calculate f18, f17. But actually, if you observe that f18, it happened to need to be calculated from this side. And the f17 will be used again in the calculation of f18. So it means that if you want to calculate f20, actually, if you divide this calculation again to the bottom, then you will see the actually there's a lot of overlapped problems, and you don't need to calculate them again and again. You just save them. Then if you need to use a computed result, you just use that and get the final result. Then there's no repeating calculation, right? So it accelerates the computation process and improve the efficiency. So this is the example of DP. So generally, if you want to solve a DP, there's two approaches: top-down approach and bottom-up approaches. And actually, overall, they are similar. What is a top-down approach? Top-down approach is that for this target problem, you just start from this problem, you calculate the split the problems into sub-problems and calculate each one. Then we need to use memorization. You just save all those calculated data and reuse it later in other places. So you don't need to recalculate again. Bottom-up approaches is that you have the target problem, but you don't start from the target problem. You start from the bottom. You start from 0, 1, 1, 2, 3. And for each calculation, you just save them and to build this tree until F20. Why this process? Then you just make a table. Just make a table like F17 equals something, F16 equals something, make a table. Then later on, if some other calculations, some problem need to use those information, you just refer to the table and get the data. Okay, that's the bottom-up approach. So now we come to this DP in our RL. Okay. Actually, the idea is simple. Actually, we already did in the last lecture. Use the value function to organize and structure the search for good policy. So means that we just update the rules for improving approximation of the desired value function. So this is the BOE, but actually this is the BOE. I didn't put the BE. Generally, initially we just use BE. Later on, we use BOE to update. Okay. So the thing is, the concept of DP in RL is that we can recursively improve the approximation of the desired value function. Now, actually, we have this evaluation or we call it prediction or evaluation and improvement process. You first do the evaluation. With the evaluation, then you improve the policy again. And this iteration again and again, eventually you reach to the optimal solution. So the initial approximation. So how we do in practice, what do we do? So this is a Bellman equation, right? We just use the Bellman equation. And because previously we just, if you look at the difference here, Bellman equation here, the original Bellman equation is that V pi s, then there's the V pi s prime. The pi, we use the subscript pi to indicate that the policy for a particular policy. But here, when we design the iterative solution, we change this subscript to time step. Okay, like a vk plus 1, and here is a vk. So it means that the previous if you want to calculate the next value function, you just based on the previous value function, right? To calculate the vk. Okay, this is how it evolves to this dp. So when the k reach to the infinite, the sequence vk will be shown to converge to v pi. Okay, so you can consider the vk is like intermediate result. So it's not reached to the v pi, the optimal policy, but in the middle gradually to reach to that v pi. So this is a iterative policy evaluation. Actually, the process is simple. You just loop through. So the particular things we need to pay attention is that now we design this is this small like error, right? If it's reached to that error, then we just terminate the process. Okay, a small threshold theta larger than 0 determine the accuracy of the estimation. Okay, so we initially we have this Vs, we just give the V, then we update based on the Bellman equation. Then we calculate which one is maximum, either this small threshold or the error we are having. Okay, so if until this smaller than the theta, then delta is smaller than theta, then we just stop the loop. So it means that we reach that, even though it's not the 100% optimal, but it's close to, very close to the optimal solution. For this algorithm, as you can see here, we have this old values VKS and the new value VK plus 1S, okay, which is here and here. So in implementation, we can use two arrays. One array to save the previous state, the value of the state, and then we, based on the previous value of state, we calculate the new states of the new value of the states, right? We can also use just one array and update the value in place. So dynamically, real time, means that once the old value is updated, then we can just immediately use the new data, new value of VK plus 1 instead of using the previous value. So it's kind of, most of the time it converges fast. And yeah, so this is some practice. So this is the policy evaluation. Okay, you have this policy evaluation. You evaluate the policy and update the state, the value of the state or state value. Okay, now we need to improve, update the policy. Yeah, actually, the idea is simple. We just, based on the state values, then we just update the, to greedily update the policy, which action to choose, right? So we need to decide whether we need to or not. So the policy improvement here, actually, but the thing is, we need to like officially or to prove that if this policy is better than the previous policy. If it's better, then we can say that if we got the better value function, the state value function, then means that the new policy is better than the previous policy. So formally, we have this policy improvement theorem. Then, so if we have a new policy, satisfy this inequality. So as you can see here, we have this Q pi is a quality of an action. So pi is a policy, pi prime. Here it means that pi prime is a new policy. It's a pi is a, what is a policy? Policy is the instruction of actions, right? Which action to take for the particular state. So this, the quality of this policy, a new policy, is equal to or larger than the V pi s, the current value function. So we have this, if we got this calculation, we got the better state values, then it need to be shown that the new policy, the new state value function is larger than the previous state value function. Okay, means that. So then the purpose is that from this condition to this condition. If from this condition, the first condition to the second condition, second result, then we can safely say that if we get the better state value function, then the policy is better, must be better. What we do is that we need to prove that why it works, right? So from the condition, you can see we just rewrite the previous one. The Q pi s pi prime s is larger or equal to the V pi s. So with the new policy is larger than the current state value function, then you can rewrite this. So rewrite this Q pi as definition q pi. It's the the return, the plus gamma v pi st1. So it's based on definition. Then we just write this at equals pi prime to here, to the subscript. So if now we can use this inequality again, because this is from the condition itself, okay? The v pi st plus 1 is smaller or equal to the q pi. So we just replace this v pi st plus 1 with this q pi st plus 1 pi prime st plus 1. So because from the original condition, this condition holds, right? Now if you just continue this process, so eventually you rearrange the order of those terms, then eventually you will see here, it just happened to be the definition of state value function, right? Expectation of pi prime, this is a discounted accumulated, like a return accumulated rewards, right? Based on the state S. This is just happens to be the state function, state value function. Okay, now if you look at here, so v pi s is equal, so is smaller than this v pi prime s. So which proves that if we have a higher the value of from a policy, then it must be that the state value is higher than the current state value. Okay, this is a proof for this process. Now, with this kind of proof means that mathematically it should work, right? It's guaranteed that as long as you have a higher values of a state, then we need to update the policy based on the higher the values of states. So we come to this iterative policy evaluation. Okay, so we have this setting, the grid word again, but a little bit different from the previous one, because now we have this we have 4 actions. They are equal probability, so like 0.5, 0.25, and we have a terminal state, like 2 terminal states on the left top corner and right bottom corner. Okay, 2 terminal states, and the other states we just use the number to name it non-terminal states from 1 to 14. So we have 14 non-terminal states, and for action up, down, right, left, left to right. Then the reward for each transition, for each movement is -1. So if you move from 4 to 5, it's -1 for this reward. Now the process is that how we apply this policy evaluation and improvement process iteratively. So this is what we do, right? So actually we did in the last time. So at the beginning, we just initialize all the values of states is 0, okay? 0. Now so the policy is also random because initially the policy is just equal policy, right? So if you stay at any state, you can have all the equal policy to move to left, right, up, and down, right? After if the k equals 1, we just update the state value function, state value for each state, right? Then the terminal state is always 0. We don't, it's like a setting based on the setting. And once you have this updated state values, then we update this policy. So the policy is that for the previously the policy is equal probabilities, right? 4 direction, all possible. For example, here, this is the state value become -1. The left-hand side is 0, down is -1, right movement is -1. So obviously, if the higher, we just choose the higher value, state value, to be the action, the policy we need to choose, because previously we already proved that. So we just choose the left movement is the best movement at the moment, okay? Then similarly to others, so from the first initial state to the first state, then actually we updated some policies, some actions of some states, right? Then we can just continue this process, calculate when k equals 2, the next time step, we update again. Similarly, all those policies are updated based on the current state value, right? For example, here, the best actions to make is left or up, right? Because the state value function is smaller than the down and the right, because those are -2, -2 is -0.7. So if you just continue this process to k equals 3, 10, infinite, so eventually, actually, your state values are kind of stabilized. Oh, someone is raising hand. Oh, okay, it's me to raise hand. Okay, so okay, when we reach to the time step equals 3, you see the policy actually already become optimal, but the state values are still updating, right? So for now, if we reach the time step equals 10, those value updated again. So, but the policy didn't change much because the relationship between those the neighbor states hasn't been changed much, because still this one is the largest among all the neighboring movements, right? Is 0. Obviously, you need to choose the left, which is the optimal policy for this current state. Eventually, if you reach to the calculate large enough, you will convert to the optimal state value, and the policy become, is already converged. So in how you calculate this those state value, then what we do is we just initially, for example, you have this pi s up, right, down, and left. All those policies you have equal probability at the beginning, right? Then you just calculate this like 0.5 times r is -1 plus 0. So initially, if you calculate all them together, which is -1, and after if we reach to the step 2, time step 2, you can calculate again based on the probability here. If you calculate still -2, if you, let me just use the, okay, so similarly, we just calculate this process, right? Similarly, so if you reach the k equals 2, you have the, for example, so just assume that we didn't, for this at the moment, we didn't update, we don't use the updated policy, we just use the equal probability, which is 0.25 times -1 plus, at the moment, if this is up here, we'll come back. So previous state is a -1, right? We should be the -1 plus 25. This is the right, left, the right, so this side. So which is still the -1. The reward, the return is always -1 and plus the previous -1. So you just continue calculate actually for the previous state. The only difference is the left, the last one. Okay, so if you just calculate, the only difference is the last one, because the last one is the 0, right? The state is always 0. If you look at here, I cannot move the screen here. Is 0, then you will be the it will be the -1 plus the state is 0. So if you calculate them together, it will be the for 5 plus -0.5 plus -0.5 plus -0.25, which is equals -1.7, which is actually 5. 1.7 that just use the 1 decimal, okay? Then you can continue update this process. Similarly, you can calculate others. This is for the time equals 2, then you can calculate when the time step equals 3. It's a similar process, okay? Okay, so this is how this algorithm works, right? You just continuously update this process and update the policy. Then eventually you reach to the converged result. So this is what this algorithm is about. Okay. So any questions? R is -1. Okay, previous here. RT. This is the reward for all transition. Whenever a movement you make, you will get the -1 reward. Okay, that's why this R is -1. So means that, for example, from this state to left hand side, the reward is -1. To up position is -1. So it means that any movement you make is -1 reward. Okay. So also based on the equations here, so actually we are updating the process. We are look through this process, look through every state, right? Each state, then we need initialize the value, then we update the value based on the Bellman equation. The Bellman equation is that this is policy, the 0.25. This one is 1 because this just sum all the possibility. This is 1, so ignore this one, just 1. Then R, this is reward plus gamma. So actually gamma, we don't consider the discount value here, we just consider 1. Then just V S prime is the neighbor state's value. This, okay. This is how we calculate this. This formula, where it comes from. So, sorry. So this pi is policy, right? Policy, we have this, the current state, we use the policy up, right, down, left. We need to sum them together. So it's like a summation, right? Summation of all the possibilities. So this is how we calculate this. So because this is a grid word, you can also consider like this is a clean robot, like you have a robot to clean your house. Then they can move to right or down. They need to choose which direction they can choose, right? Up, right, and down. And the robot need to decide which one. Then it has some goal to cover all the spaces in the house. Then which the minimum battery usage or something. Then which one is the best path to use? And there's obstacles around. Yeah. So what we are doing here is just use the Bellman equation to iteratively update this process. Okay. Any other questions? So currently, at the moment, we just use this. We update them. As you can see, when we did the calculation, I just used for example, when I calculate -1.7 based on the previous states, right? Then we got this value. Then when I calculate minus 0.2, it's also based on the previous state. So the policy update, we just greedily select the one which is the higher, the updated policy, based on the higher the value, state values, right? But actually at the moment, we just use the original BE instead of BOE, Bayerman optimal equation. Later on, actually this part will be updated. So we'll be accelerating the calculation process, okay? In this case, we need to calculate every possibilities. If we use BOE, we just select one that is maximum, okay? Yeah, so the policy iteration. So this is like final, the overall process. So you have the evaluation and improvement, continuously. So it's like if you look at you have agent in the environment, you have this circle, right? Circulating this, you have evaluate the state based on the updated state values. Then we update our policy. We make a new action again, continuously. So this is what we did, right? We calculate these state values, and there's a termination condition. Whether we reach to that accuracy, if we reach that accuracy, then we just stop. Then policy improvement is that we for each state, you see here the loop, the iteration is for each state. So we need to iterate all the states. Then for this particular state, then we get this based on this state, we have this the action based on the pi, there's no prime, right? Means that this current policy, then we get this action. With this action, among all the possible action, then we just argmax the Bayerman equation, the quality function, right, of the Bayerman equation. Then update this pi s. So it means that it just mathematically or like an algorithm description of the previous step we did here. For example, from here to here, this is the algorithm description of that process. Initially, you have these four possibilities. Now you just choose the one that maximize the current state values, which is minus 0.7, right? You just ignore other possibilities. Update, only use the move to the left. This is what it's meaning here, okay? If old action isn't equal to the pi s, then the policy stable give the false. So means that, okay, if actually there's old action, the new action. So this new action has been updated by this argmax, right? So then we just check whether this old action is equal to the new action, new policy or not, based on the new policy. If not, the policy stable become false. So just actually this is just condition. Only when this policy stable become true, then we just stop, because means that there's no update anymore. Means that we already reached the optimal policy. Okay, if the policy is stable, which is true, then stop, return the state value function and the policy. Otherwise, we go back. So you see here, s go to 2, which is the evaluation, right? Policy evaluation. So it's like this circle. We evaluate, then we do the improvement, check whether the policy is stable. Otherwise, we go to 2 again, do the evaluation, and check policy again, keep updating. Eventually, we reach to the stabilized policy. Okay. Any questions? So yeah. Yes. Yes. Yeah. So I guess the policy, you mean the stable policy here, right? So yeah, for that case, maybe we cannot reach because the policy already stable at some point, right? We just reach to some particular time, then it's just stopped. We don't need to evaluate again, right? But for this purpose, we just want to show you the convergence, the converge to a stable, optimal state. So if you use that algorithm, it will probably stop here or here somewhere because we already reached to the stable states. So it's also possible that even though, because this evaluation improvement, even though we have this, we may not reach to this. So the policy of the update or optimization will be stopped here, but the value iteration will still be going on. Because once it will compare, it already stabilize. It will not do that again, the improvement. It just update the set value. Okay, if you look at the algorithm. Because there is also condition here. It needs to reach to some accuracy to stop this evaluation. Okay. So it's like two iterations, right? Two iterations mutually affect each other, but not always affect. Only when it's not stable, it will affect here. If it's stable, this process will be stopped. Then this process will still going on, right? So because only when policy is not stable, we go to 2. But if it is stable, this process will be stopped, will not be executed. Then we only execute this part until we reach to an accuracy. Okay, the predetermined accuracy means that we reach to some optimal state. Okay. So now we look at some drawbacks of the policy iteration. Is that so? As I mentioned, that we use the Bayerman equation, which is highlighted here, to update. Means that actually we need to check. So you see the loop. Every time we need to check every state of the target environment, right? Every state. This loop 4 and the loop 4. So it's like every time when you do the evaluation update, you need to check every state again, like a scan all the environment again, scan all the environment again. So it's like bring a lot of burden for calculation. Then the problem is that need to sweeping all the states, like update every state value, right? In that case, actually now we can use the BOE, so Bayerman optimality equation into the update rule instead of using the BE simply, okay? Okay. So we have this, we call it the value iteration for estimating this pi. So what we do is instead of using the BE, we use the BOE. That means that we just select the maximum value among all the actions to calculate this value. So we will see it, for example. So others are just same. I'll put a deterministic policy. So yeah, this is also argmax. So it's a simplified argmax. So just greedy, choose the greedy actions based on the current state values. So the thing is, what's the difference here? The difference is that we still need to iterate through the states, but now this time we don't need to calculate all the neighbors. We don't need to put all the neighbors states together. We just select the one that is the maximum. Now we come back to this greedy word. Well, the calculation, the updating condition is to come this way. Previously, we need to sum all of them together with the probability of the action with the policy, right? Now we just select maximum one. We have 4 items, 1, 2, 3, 4. So R plus VK S prime S 2 prime, 3 prime, 4 primes means that the neighbor 4 actions, 4 states of the neighboring states, right? So we just select that has the maximum value. Then we just update the current value function. This is the difference, right? Previously, so if you look back, what do we calculate here? We need to sum all the probability with which this policy, right? Up, right, down, left. Now we just select the one. We have 4 items, 4 parts, 1, 2, 3, 4. We just select the one among 4 items. We just select one that is maximum among the 4. Okay. It's kind of increase the convergence speed. For example, so now if you actually, this is from the textbook. If we use the value iteration, now the value here is different, okay? Different from what we calculated before. Previously, we just based on the BE. Now we calculate the values based on BOE. So if you look at here, what we can calculate is that, let me show you. So initially we have this 0. So what do we do? For example, we want to calculate this. For example, we want to calculate this the first one, the first step. So the previously it was -1, right? This is still -1. So we just if you look at this BOE, which is 1 plus the neighboring initially previous all the states are 0, right? 0 plus 0. It need to be if you know the Python, then you give the multiple items, then select the one with the largest. So is that, so you have max, then the first one is a -1 plus 0, because initially all the states are 0, right? Then this is the first item. The second item is same, plus 0, -1 plus 0, -1 plus 0. Among them, select the maximum. Actually, they are the same, right? All are -1, -1, -1, -1. So the maximum is just equals -1. So the first step is the same. All status are the -1. But the thing is, the second step is different. Let me clean. So the second step is that, so the value is different, right? Okay, so if you have, for example, we want to calculate the state value of this -1. Okay, so just clarify some questions to the time. So one question is that, so because if you consider the folder state, so the folder state is up, they will constant to the current state. So for example, you calculate the first one, is up, you'll hit the wall, and constant. Okay, to the current state. So means that VK as first is the VS itself instead of the other. Yeah, so also, actually I used the same example from the textbook. So the first example is the one how we calculate the difference from the policy evaluation. The next one is also in the textbook, like now we are using the value equation for the value here will be changed. So this value is not correct. So it's done value iteration. Even though I'm using the same value. So this one minus 1, and this one, remember, I posted, this will become minus 0.7. So it's like a converge faster than before. You can try different ways, different ways with this POD method, okay? And we'll see the difference of the updating. And similarly for this example, if you look at the obstacle, they are also the wall. So if you hit the wall, it's constant. So you have the action, the word, but the state will be the head and the time state. Okay, this is the second example. Okay, so let's continue with one more lesson. And yeah, okay. Let me check my microphone. Yeah. Okay, so now we come to a new type of method called Monte Carlo method. Why we have this method? So so far we learned about the environment, the NPT environment. So you do have the only knowledge about the environment you're dealing with, right? So previously we assume that you have a complete knowledge of the environment. What if we don't have this much? For example, same example, you have a clean robot in a house. And the first time, you don't want to input your house map right into the clean robot. You will explore your house based on some sensing data, like laser sensing or some ultrasound sensing. You check the boundary area of your house. Then we move the first several trials, they will use your house map, right? Then how the robot did, you just keep trying different locations, different directions, and eventually combine all those information, then use the environment, the knowledge about the environment. So Monte Carlo methods are those kind of methods, like build the environment based on the experience. So in short, this is MC method. We just need the experience, sample sequence of state, actions, rewards, of actual simulated interactivity with the environment. So if you remember, we learned the MAP problem, right? Multi-arm bandit problem. So in the MAP problems, so you have a set of the machines. You need to decide actually which machine to choose, right? But actually each machine just has one state. You don't have, if you choose that action, the state is also fixed. So that's just
state is left. So in the a little bit different from the MAP problem is that now each arm, each machine will have multiple states. Okay, and also machine will have intercorrelated. So the state can be jumped to another state to another machine. It's like a high level of map problem. Okay. So, but the idea or the concept is similar. What you need to do is that this error and trial, keep the test the different possibilities. So, what are the objective of the MC prediction? So first we need to do the prediction, then we can do the update or improvement. Prediction and improvement. The objective of the MC prediction is that we try to learn a state value function for a given policy. So if you see that so far we always deal with a state value function or state action value function because based on the RL framework, right? We have the agent, we have the environment. And policy for the agent is the brain of the agent. The purpose is to learn this policy, find the optimal policy for this environment, for this particular problem. Then for the policy, for updating this policy, we need to rely on this state value function and the action value function. That's why we keep working on the state value function and action value function. So how we can find a better solution for different problems. Okay, so still here our target is to learn the state value function for a given policy. The key idea is simple: averaging the returns observed after visit to a state. Averaging the returns is like an example that I gave you. So the robot, cleaning robot, move to your house, try to get the sense how your house is configured, layout, the living room, bedroom, and the kitchen, all those stuff. Need to just move there, and then using different sensors to check your data and build a map for you, right? So it's like similarly here, it's like going to visit the state and collect the data from the state. And we visit the place multiple times, continuously updating the return. So formally, we estimate this state value function, V pi s, given a set of episodes. Now actually we are introducing a set of episodes, which is different from the previous setting. Okay, previous setting is that you have the overall information about the environment. So you just deal with this environment. Now you don't have the environment anymore. What you need to deal with the different episodes. It's like we play. Okay. I don't know. When I prepared the slides, I just remembered the TV episode I watched before from US. So it's like there's an AI to control everything. So it's like there's the one actor in the TV episode. It just has the earphone to receive the instruction from AI at a particular location. You need to do some action, make some decision. Either use the window to escape or use the door to escape. So it's different action. So what the AI did is that in a short time, it simulates every possibilities to check which behavior, which decision has the highest probability that the people can escape the current situation. Okay, that's what is happening here. So it's a set of episodes. Each episode is a play of the environment to check the appearance of this environment. So we given a set of episodes obtained by following the pi in Python's locus. So we have a set of episodes. Each episode has a timeline from the beginning timeline to the termination timeline. Another episode from beginning to the end. Another episode, multiple episodes. Okay. Then each occurrence of the state S in the episode is called a visit to S. So assume that because we don't know the information about this environment, even though the state information we don't know. So we only know that for the state is visited, so this state is the information we got. we call the visit to the state. Now we just differentiate the first time visit or the every time visit. So we call the state to be first time visiting, just simple, first time to visit as. There's a slightly difference here, so we'll look at in detail. But you just remember what is the settings here, right? You have a state value function. You are given a set of episodes, different replays, different possibilities, and based on the current policy, passing through the states, different states, right? Then we define the first visit of each state. We call it the first visit to test, right? Now we have this so-called first visit MC prediction. Prediction is to predict because we are using the prediction because we don't know the environment information. We need to predict the state value. So the final goal is to learn the state value function, okay? So as you can see here, the final goal is to update the BFT through this iteration process. And there's a little tricky part for this so-called FVMC prediction. Okay, let's look at detail how it works. So from the beginning, so you have a policy to be evaluated. So we are not sure this policy is good or not. So actually, initially the policy is dominant policy. Yeah. So actually, so here we just have this policy. Then initialize the state value. If you consider it a grid word, initialize it with any number. So sometimes we just give 0. Return S is a list, empty list. You will return the state, and each item is a state accumulated reward, okay, or return. Each state will have a return. Each state will have a return. It's a list. Python is a list, right? Each item is a state reward. Then we just look forever for each episode. So here each episode means that actually we have 2 loops. The first outside loop is for every episode. The inside loop is for the timeline of the particular episode. Now, from one episode, then we generate a sequence following the time. Because initially the policy time is just, they have an existing policy because we're gonna update the policy. But initially we have the initialized policy. For example, in the grid one, the initialized policy is just equal probability of 4 directions, right? So 25. Initially, we just based on this probability, we generate a sequence until some terminal state from S0. So, for example, at the beginning, you are in the S0, then you made an action A0. The action A is depends on the pi, positive pi, right? Then you got the reward R1. So now you are in the new state with the reward. This reward is from the previous state and action. Then you are in the new state S1. The new state, based on policy, you make a new action A1. You get the next new reward in the next state R2 and S2. Make a new action continuously until you reach to the predefined terminal state, which is we use T. Okay. So before T, so there is a T minus 1, AT minus 1, and RT get this reward. So if you get this reward, then we just stop. Okay, we don't do anything. So this is generate episode. This is the timeline. State action reward. State action reward. You will jump from one state to another state, another state, another state. So among these states, there could be a state can be visited multiple times. Okay, for example, this S1 can be visited multiple times. It can jump back to the previous state has been visited. So if you consider the grid world, if you are in the location, it is possible that you make a detour and come back to the original state and move to another location. Okay. Now we initialize this return t equals 0. So this T will record the average, okay, the return for us, accumulated. So look for each step of episode. So now you look at here, there's a slightly different. Look for each step of episode, T equals T minus 1, T minus 2 until 0. Actually, we now reverse the timeline from the ending terminal state back to the state the first time we visited a particular state. What it's doing here, T equals T minus 1, T minus 2 until 0, which is we move from the terminal state back to the starting time. Okay? Now, with this in mind, we calculate the return. So the current return with the discount rate plus the accumulated reward. The reward in each step. And update this T. So here the condition here we use the unless ST appears in S0, here is T minus 1, which means that if ST is not in, means that we haven't counted this ST before. So this is the first time to count a particular state. Then we put this ST, we put this T appended to this list. As you remember, return is the list, right? Now we do the average. Average is how many times we calculate this state. And the return for this state is accumulated. This is how it is calculated. Now, but actually, when you look at here, it's a little bit still confusing. So, for example, there's an example. You have let's assume that we just have three states: S0, S1, S2. We have two episodes: episode 1, E1, E2. For example, the first episode, S0, you visited, got the return G as 0, and S2 is also visited with G as 2. Then the next state, next episode, you visited S1, we got the G as 1. We all count the first visit, okay? The S2 equals G as 2. So actually, the S2 has been visited twice in each episode because we only count the first visit, right? So now the S2, GS2, the T2 GS2 will be sent to this list, and then we do the average. So eventually the return, the state value of a particular state will be the average of those the experienced returns. Okay. Still, it's a little bit abstracted, right? It's not that clear. Let's look at the example, how it works. Actually, because this algorithm is from the textbook, when it written here, it's a little bit confusing, but they use unless ST appears in S0 because T minus 1. So I just interpreted it as it actually is the condition of the first visit. Because the state can be visited multiple times, we can come back to the same state. So, but in here, we just count the first time visit. Also remember that from one state to the end of the state, so the first visit until to the end, that the reward or return of the state is accumulated reward from until the end of the state. Means that for a particular state, the G actually is the accumulation of all the rewards until to the end. Okay. So, for example, so this is another description of FV method, FVMC prediction. So the process is similar, and the condition is also similar. So actually, how to calculate. So the problem is that I just try to clarify what is exactly doing here. If you look at, you have an episode I. For the particular episode, I episode, okay? Then actually you have two subscript. Episode is the I episode, and the second is the time step. For this I particular episode, there is a time step. So you have multiple episodes, right? Then define this GIT. For a particular episode, you have the accumulated rewards, which is the return, right? So each time step T until Ti. So it's similarly, So the end of this episode, and the P. But actually, we did not do the reverse. Actually, we need to count the reverse because the reward may be accumulated. Right? Then this is the first time T that we did it in episode 5. Then we just calculate the count, how many times we have visited among all the episodes. Then increase the total return, accumulate all the return in every episode, then calculate the average. Okay? This is how we say this is the first visit MC prediction. Then there's also for so-called every visit MC prediction. What will be the process? The process is that this condition will be removed. You will not check whether this is the first time visit or not. So the same state can be visited multiple times in the time on one particular episode, right? So it means that you will accumulate multiple times of a particular state, the value of state. So, example, okay. Assuming that you have so you have this episode 1 and 2. Now the property is good. First, explain A plus 3 means that you are in the state A with plus 3. Okay. So what do you process the formula? A try actually all the time. Anyone? Also, So for the first episode, so you need to check the first visit complete, which is 22. Now we just calculate. One, so first visit from the beginning, two plus 3 plus so this is the internal. So now we come back. So you know internally how it works, right? The tricky part is that you need to, for example, you reach this state, you want to calculate S1. Now you need to actually get accumulated all the state from this S1 until the end combination. Okay, then calculate this accumulated return. Okay. So you see here the RT1 actually is all the generated sequence of the reward, right? The reward from this generated then append this. So it means that every state will have if it's just one exon, just put one. If it has multiple exons, you need to divide it by how many exons. So now we just consider the first visit exon. Okay. Now how about every visit MC? Every visit MC. Actually, every visit MC is going to talk this projection algorithm more later in the later lecture. But moment we can see how it works later on. Look at the detail for what's the difference effect. So what is every visit MC? Every visit MC means that actually this part is here. Okay, there's no this condition. If SP is not in, so this condition is not held anymore. Now we just count every S of the state that happened with visit in the timeline. Okay, what we do is here, let's use the second example here. Okay. So now we can every visit and see. So now, so the E1 will be, let's compute the VS. So actually there is a multiple visit, right? A, the first time, second time, third time. A has been visited 3 times. Now what we do is that for the E1, we need to do is that plus 3 plus 2. So the first one is the same, and plus minus 4 plus 4 plus minus 3. This is the first visit. The second visit is the plus 2 plus minus 4 plus 4 plus minus 3. The third visit is plus 4 plus minus 3. So we have 3 visits, right? three visits. So we have three values. The first one is 2. Second one will be -1. And -1. The third one will be 1. So we have three visits. Okay, now this is for E1. Now E2. For the E2 will be same because we only visited A once, right? Down to 0. So what we do is that we need to sum them together. 2 plus -1 plus 1 plus 0 divided by 4. We count 4 times, right? Because A has been visited 4 times. The first episode, E1 is visited 3 times. The second episode 2 is visited once. So divided by 4. Which is equal to 45. Right? So this is every visit. EV times equality. Similarly, so it's slightly different. EV. So at the beginning, when we use the environment, so we need to build those dynamics of but the thing is now if we don't have those what is here so you because you have the any episode, then you make them. So feature here of that's also the if you feel the application. So now we want to how we value action. MC prediction for the predict statement. Now, actually, it will be more useful to check whether the action, quality of action, okay. So now we want to check, estimate the value of action, which is the action value function. Okay. So, but the thing is that there is one issue, as I mentioned in the previous idea is that you can see check the whole time of each action. But how can we guarantee that? How can we guarantee that every thing, every action has been checked? Because we want to know
the information of this environment, right?
We want to know the information, but we are not sure that, visit every state, check every action of the policy. We are not sure. For that purpose, we need to we need to design some method to guide the agent to start in multiple different every state action pairs. Then that every state action pair can be selected, can be experienced to know what is going on from that state action pairs. Okay, then we call it exploring stars. So we need to design some process that can explore every possibility, even though we don't want to, So to remove the biased visits, right? So let me switch a little bit to the microphone. Okay. So this is the purpose of this to make it more robust of this MC estimation. We need to put some mechanism for this exploring stars. Now, previously we do this MC estimation for the action value. Now we do, after this action evaluation, then we want to control, actually improvement. Similar to the previous one, the DP, you have a policy, and you evaluate the state value function, update the state value, and based on the state value, you do the greedy choice, maximize the current, based on the current state values, you maximize the policy. Based on then update the policy, which policy is better, improvement. And similarly, so the MC control, the control here is to update the policy, it's like improvement. Even though here actually, because we don't know the complete knowledge of the environment, that's why we use control instead of the updates or like improve, because we are not sure whether we are improving or not, but we are using control whether the policy has been controlled. So MC control means that we approximate optimal policies. To means similar to the previously in the DP improvement. Okay, update the policy. Then we can follow the idea of the generalize the policy iteration with two assumptions because we want to make it work, but to make it work, there's two assumptions need to be made. The first one is exploring stars. Because if you have this assumption, means that the environment, every state action pairs will be experienced, will be explored. And infinite episodes means that you have unlimited resources or like times to try, to give enough trials to see this environment. Okay, these two assumptions. Now, based on this this setting, this evaluation and improvement process, we design this MC exploring stars. So in short, the MCES algorithm. So what we do is that, so as I highlighted with this blue rectangle.
So because we just put those two assumptions into this algorithm. The first one is the assumption. So you the initialize, so you will see the initialization similar to the previous one. So you have a policy. So initially we just can keep randomly, arbitrarily the policy. Then the quality of the action is also arbitrarily set and returns the empty list we need to get updated, right? So then this exploring ES condition assumption is that choose S0 and A0 is a state action pair randomly such that all pairs have probability larger than 0. Means that for a particular state, then we do the action. So every this state action pair need to be experienced. Then we generate an episode. So similarly to the previous algorithm, we did the first visit, right? FVMC estimation. This one, right? Prediction, FVMC prediction. Now the other the same, we generate this sequence, time sequence, from the state S0 until to the end terminal state. Then we initialize this G equals 0, loop through every step of episode, T equals T minus 1, T minus 2. So it's similarly to the previous one, right? So from the end to the beginning to the to the beginning. So the backward from reversely, we from the end to the beginning. Then we calculate all the returns for for every state. And this is condition is holds for the first FV, first visit state. Then we add one more, which is the greedy action, right? Greedy argmax. So that we select an action that maximize the quality of the current state action pair. Then we update this policy. So it's the last one is the same to the previous DP argmax, right? So following this pi should follow the greedy Q. It means that maximize the current state value. Okay, this is how MCES works. The thing is, what if we don't have this ES assumption? Exploring stuff. This exploring stuff means that if you means that you need to randomly choose all pairs, right? All pairs have the probability to be chosen. If we don't have this condition, how we can do? Actually, yeah, sometimes most of the time it's difficult to assign. I mean, randomly to assign those probability for every state action pair because it may be very burdensome because the state can be a lot and the action can be a lot. Then the combination is also a lot. Then the computation, the load is high. So then we have actually two type of approach to deal with the MC control here. I also need to emphasize that MC control here, it means the update or improvement, okay? MC control without ES, two approaches, on policy and off policy. Most of the time, if you read some research paper or some real world applications, they usually use this on policy, off policy, or something. Some on policy, some IR based method or something. So on policy, off policy means that on policy means that we use this model itself, the agent, the policy it has, then to make the decision. So means on policy. Evaluate or improve the policy used to make decision. Means that we just use the policy we have now and improve the policy, okay, made to make decision. Off policy means that we evaluate or improve a policy different from that used to generate data. So you need to pay attention to here. I use the improve the policy. The policy means that the policy of the agent currently have. Then off policy means that evaluate or improve a policy. Means that any policy we need to design, we need to have a different policy, okay, with the policy that the agent can't have. We call it off policy. Means that off policy actually has two policies. A policy it has currently and another policy. Okay. So if you look at this, so let's take a look at the first approach. The first type approach called on-policy control for MC. If you remember the map problem, so we had the epsilon greedy algorithm to choose to make the decision. Then you have because you want to explore all possibilities instead of exploiting the current knowledge. So similarly here, we can just add the epsilon greedy some probability to select non-greedy actions to alleviate or mitigate the previous this condition. Previous condition is that we need to assign probability for every state action pair. So they have some probability to be visited, to be executed, to be run. But now we just assign all non-greedy action will be chosen with some probability. So they have some uniform probability. So now we divide the actions from greedy actions and non-greedy action. For non-greedy actions, will be chosen with a probability based on this definition. Epsilon is a small probability and divided by the set of the action, the size of the action. So AS means that for this set S, the size of action, how many actions we can have, then divided by the size of actions. So this small probability divided by the size of means that for those non-greedy actions, so they have all those probabilities, the equal probabilities to be selected. Then for the greedy actions, will be chosen with the probability in this formula, 1 minus epsilon plus epsilon divided by the size of the action set. Okay, so in this way, we design this so-called on-policy FVMC control. You see here, we kind of gradually adding new things to the basic algorithm. Initially, it was FVMC, the prediction, the FVMC control. Then now we are coming to the on-policy FVMC control. So the overall process is same, and then you see here the exploring star ES condition assumption is disappeared. We don't put those conditions there. We don't need to assign probabilities to every the state action pairs anymore. Instead, what we do is that we added this on-policy the way mechanism here. For all A belongs to AST, we can update the policy, whether it's a greedy action or non-greedy action with some probability with this setting. Okay, so if you compare this algorithm with the previous, so previously we did so the MCES, the estimation. So we have this ES condition. There's no after that we just use the greedy the action, right? Choose the greedy, update the policy greedily. Now we update the policy with some probability of from non-greedy actions. Okay. So this is the on-policy FVMC control. And now actually we are seeing different kind of solutions or algorithms deal with different situations and to improve the process, right? So now this is for the on-policy FVMC control. Now let's look at another method, which is off-policy prediction.
we so-called importance sampling. So as I mentioned before, what is the on policy? What is the off policy? On policy is that we just work on the current policy we have. Our policy is that we will have another policy, a new policy that will mimic, that will simulate the original policy. Okay. Now based on the previous setting, we have a dilemma here. We try to seek action value based on the optimal behavior, but we also need to choose non-optimal behavior for the optimal actions. It's like so this previous actually what it is saying the status here. We want to get the optimal status, but we need to choose non-greedy, non-optimal actions to explore. That's always so throughout this IR course lectures, the process, the framework, we always have this EE trade-off, whether you want to do the exploration or exploitation. Okay, so now this is the dilemma here. Now then we can use so-called off policy. Here is mentioned. Another approach is to use two policies. One for learning and become the optimal policy called target policy. Target policy. The other one for exploring to generate behavior called behavior policy. Okay. So it's like the one target policy is the one we try to reach. The one we are trying to learn this policy, the target policy, which is optimal, will become optimal. Another policy is that we use this policy for exploring the environment to generate new behaviors. So the thing is that the two policies need to be statistically need to be identical, okay? But even though actually they are not identical, because you cannot just generate, because we don't know the environment, the complete knowledge of the environment. We don't know those distribution of the environment, the different status and actions, which the probability. So actually all those are estimated. So now we call this kind of approach of policy learning. Now actually we are using learning, the term of policy learning. We need to learn this of policy. So here we introduce the one term, which is called importance sampling. Importance sampling is a general technique for estimating expected values under one distribution given samples from another. So you can see importance sampling. So for example, you have a distribution for some particular target. Now, actually, for this target, you don't have the knowledge about this distribution. You only know some points, roughly the data of this distribution. Now, important sampling, the task of important sampling is that we just based on the current data we have, then we estimate the value based on the current distribution, even though the distribution itself is not complete, but we just try to guess or estimate the expected value of the one condition. And there's some process how we can do the importance sampling. A little bit tricky here actually. So we also developed so-called importance sampling ratio. It's like you have a target, the policy, it has some distribution. You also have this behavior policy. So initially it has some distribution. You can initialize it. So now this target policy, so we need to make some ratio that we sample some data from the target policy and sample some data from the behavior policy. So we call it importance sampling ratio. Then actually researchers already developed some this kind of a process, the formula here. Now, giving a starting state st, the probability of the subsequent state action trajectory. So you have a trajectory. Okay, there's a misaligned here. Okay, then you have at st1, at t plus 1. Then based on the policy, any policy. So actually, the probability of a policy is that the probability of a sequence of based on the given state and action policy. What is the probability here? Is that you can like rewrite this probability into multiple parts. For example, you based on the here in detail is that we want to check for a state and an action, a policy that it generates a particular sequence. The probability of generating this particular sequence. What is the probability of here? Now we kind of decompose this probability into multiple small actions. So firstly, for this state st, at, we follow this policy. We make we select an action based on this policy times the state transition probability. So it's like two-step processes, right? So as I mentioned, I write down here two-step processes. First, select an action based on the policy pi. And second, based on this action, move to the next state. This is the transition probability of this state, the two states, right? So you can continuously write this process from the time t until to the terminal state. So this is one, two-step. First select the action. Based on this action, then we have transition probability, because this transition probability is from the environment. Then again, for the next time step, we again select an action based on the policy. Then there will be a p st plus 2 st plus 1 at plus 1. So it's like again the next transition probability to the st plus 2. So you can write continuously. Eventually, you can write in the short form. So you have because there are times, right? This symbol is times all of them together. The product, so of all of them together, the policy, your state transition probability, then sum them together. You have now we just can calculate for a particular state with the policy, the sequence of generating the probability of generating the sequence will be equals to this. Yeah. So the thing is because we are dealing with, but actually the assumption we are having is that you need to have the state transition probability, which is this one, right? From previous state to the next state with the action. But the thing is we don't have the complete knowledge of the environment. Actually, this one is difficult to get. And we only know that we are the agent. Then we have our policy here. We only know actually this policy. So this part actually is difficult to get, or partially we have. Okay. Now we just like product all of them together. Then you will get the probability of the. Actually, if you sum like times them together, the probability is very low, right? For different sequence. If you consider this one can be in one episode, there's another episode, another episode. So each episode, it means that the probability of a particular episode based on the current state and the action, the policy. So this is actually, you can consider it a probability of an episode happens. Okay, so now based on this derivation, we have the probability of episode, let's say the probability of the sequence. Now we can calculate the important sampling ratio, because actually we define here, we just because that's the previous the ratio, the probability of the sequence, right? Now we are calculating another the probability of the sequence based on policy B instead of pi. So B is behavior, we use B. Behavior policy, we use B. So this is another policy. Then we just put them together, compare, and so this common part actually is not related to the agent, the policy itself. It's just the environment information. It will be cancelled, right? Eventually, we just have the two policies information. Okay, this is the target policy. This is the behavior policy. Then we just to get the ratio between two of them. Then this is how we define this. The importance sampling ratio, we use the rho t to t minus 1. So actually we specify the termination state, which is t minus 1, from the particular time to the t minus 1. So you have this timeline from the t until to the t minus 1. We define this ratio. And yeah. So since the return, I mean, now actually we are dealing with the second B. You see the B, VB is the behavior policy. So this is based on the definition of the state value function, right? So VB, so because this policy we have here, then we want to get the expected value of which is the expected return based on the state as the status. So actually this is the definition, but actually it does not reflect the expected return of the target policy pi, right? So now we use this ratio, the ratio we just get to transform this VBS to have the right expected value, which we rewrite this form into this way. So we put this rho small t to t capital T minus 1 is this GT. So it's like what is written here actually? You put this part to here. Actually, what is written is here is that you just get partially of this GT. Okay, not all the GT because the GT is from the VB. GT. So if you look at here, this GT actually from the behavior policy instead of from the target policy. But we have this ratio. We put this ratio here. We just sample the behavior policy based on some ratio. Then we can like approximate the target policy. So yeah, okay, a little bit complicated, right? Kind of a very let's say carefully designed process. And now since we have all those background, now we just do the setting since we don't have enough time. Okay, so we may continue the contents from next lecture. So just we can stop here. So we just skip the remaining part and we will resume the knowledge from next lecture. So the thing is, eventually we do this importance sampling based on with update this VS based on the VB, right? Summary, okay. So far we learned this DP for IR in IR, so it's a relative method. So we have value iteration. We also learned the MC method for approximating state value and sampling the sequence of state action with many episodes. So the key idea is that sampling sequence of state action with many episodes. So if you look at the overall big picture, you see the DP and the MC. The DP is that it check every possibility, right? DP check every possibility, and the MC it check the going to deep, check the deep, but with many episodes to explore the environment. Then in the next lecture, along with MC, in the next lecture, we're gonna learn this TD learning, temporal difference learning. It's like it's between DP and MC. Instead of going to so deep, we just check the time difference between two states, the value difference between two states, and do the learning. And another one is The extreme one is the brute force way. So we do the exhaustive search. It's like traditional algorithm. Okay. Okay, that's all for today. Thank you for your attention and see you 2 weeks later and have a good to the holiday. Okay.